In this video, I'm going to show you how we can generate simple loops within our assembly language. Now, these looping structures are absolutely fundamental if we want to be able to call our CPU Turing complete. Now, above here we have our Visual Basic Code Editor, and over here we have our CPU. So let's start off by creating a new file, and we're going to call this file ctm for code the machine underscore loops underscore labels dot asm. So that's loops and labels. Now we know we have to start off at origin 0 cross 8000. Now what we want to do is just increment register R0 by a value of 1 and just keep incrementing it. So it's hardly surprising that the command we want to use is inc for increment, and we want to increment R0. So this just adds 1 on to the value of register R0, and we can see that if we put the end here and we go terminal, run task, assemble file, and you can see it says assembly successful. So we can get in here and go simulate, right, reset the simulation, reset it, and we can go in and edit contents, open, and this is the file here, ctm underscore loops underscore labels dot mc for machine code. And now you can see the commands here. It's maybe a little bit small, but I think you can make it out. So the first one is 4400, so this is just increment R0, and then 5800 we've already seen, that's the end command. So we'll go up to the top level, simulate, tick enabled, and there you go, it's put 1 in register R1, and that's the end of the code. So we can stop this here, simulate, we'll reset the simulation, ready for the next simulation. So that's us able to increment, but we don't just want to be able to increment, we want it just to keep counting. Okay, now in order to get it to keep counting, we have to go back to this line. So we can use another command to jump back to that line, and it's hardly surprising that the other command is jmp for jump. Now we could tell it to go back to that very line there, but we would have to know what that line is. We would need to know whereabouts in memory that line is. But we could work that out easily enough for this small program, and let's just do that now. We know that the program's origin is 0 cross 8000. We know that this increment command is 1 byte long, so this increment command takes up one of these bytes at 0 cross 8000. Okay, so that in effect is the address of that command. So we just need to tell the jump to go back to 0 cross 8000. So it never goes to the end here, it goes to here and then jumps back again, and it just keeps looping around forever. So we can go terminal, run, assemble, and you can see it says assembly successful, and then we can go in and load this program in, edit, open, and this is our program sitting there, open, and you can see that we have the new code here. We've got our increment command here, the next one is the jump command, which is 0c, and then the next one is telling it where to jump to. We're going to jump to the memory location 8000, which again is just back to here, so it just goes from here back to here, and it just goes around that loop, and we don't even use the end command 5800. So we'll close that, design, and then we'll go in and we'll simulate, tick enabled, and there you can see it counting up. Now because I'm recording this at the same time as running it, and I don't have a particularly fast machine here, it runs a little bit slower. So if you are running it on your machine, it may well run a lot faster than this. But you can see it just counts endlessly through the loop, and in fact we're going to have to simulate and stop it and force it to stop, and then we can go reset, we can click the reset, and it's ready for the next program. Now, this isn't particularly convenient because if you're writing code and you're writing large reams of code, then you don't want to have to remember all of the addresses that you have to jump back to. I mean, that would just be ridiculous. So what you want to do is have an assembler, and within the assembler will take care of all of these jumps. So we can do that by using a label. So rather than saying we want to jump back to 0 cross 8000, we can set up a little label here. So we could, for example, call the start of the loop, what you want to call it, count. And if we put the semicolon there, then we know that this is a little label. Okay, so we must put the semicolon. So we don't go like that and put a space and semicolon or anything silly. We put count and then a semicolon. And that means that we can get in here, and what we'll do to make it nice and neat, if we're going to have this little looping structure, I think we'll indent these, okay? And we're going to jump back to count. Okay, now we don't even need the end here because it's just going round in a circle. So that's us generated a little label, and if we go into terminal, run, assemble, and you can see it says assembly successful. We'll go back down in here, edit, open, close the window, design, user panel, simulate, tick enabled, and there you see we've got the same process of running through all of the counts. It's just in an endless loop, but we've done it without having to understand anything about where any of the code is held within memory by using labels. Now that's all very interesting, but if we were to stop this for a moment, simulate, reset, and get it ready for the next simulation. Now, we don't necessarily want to just count up indefinitely. We want to count to a particular number. So let's say we want to count to the number 10, okay? Then what we can do is we want to be able to compare the contents of the register R0 with the number 10. And whenever the contents of register R0 are equal to the number 10, we want it to stop. So how do we compare these? Well, it's hardly surprising. We use a command called CMP. So CMP for compare. And we can compare the number 10. Remember, it has to have a hash because hash tells us that it is a literal number. If it doesn't have the hash, it thinks the 10 is a memory location, and it will try and compare the contents of a memory location 10 and not the number 10. Okay, so that's the way the assembly language works out. So compare 10 with the contents of register R0. Okay, now let's say for instance we did that comparison. We would have to know that it actually was equal to the value. So whereabouts does it actually do this within the CPU? Well, if we head down into the CPU here and we go into the arithmetic logic unit, now it's a little bit small, but you should be able to see up at this point here we actually have a comparator. It has a greater than sign at the top, an equal sign in the middle, and a less than sign at the bottom. And we take out a couple of the lines, and this happens for every command that we run through, okay? And these are, the one at the top it says A is larger. So A is the source, so it's the very first value, so that's a value 10. And it also tests whether the value is two values are equal. So we get a test for larger, we get a test for equal. So let's chase these up and we'll see whereabouts they go to within the CPU. So this is it coming back out of the ALU, and these are the lines here. There's actually an equals and there's an AL, which means A larger. And this heads into this little section here, and this is just a little register. And it holds what we call the flags. Okay, so these two values are two of the flag values, and they get flagged up every time we run through a command. Of course, we don't always necessarily need to use the flags, but they're always there after each command. So in this instance here then, what we want to do is we want to check and see whether we've got a value of 10 in register R0, that is if those two are equal. So we need to test the equal, and then we need to do something with that test. So what we want to do is just basically jump to the end of the program. So we could say JE, okay, so this is a new command. So this is this is another jump command, but it's a jump command with a test in it. So it jumps if the two values, if we get an equal sign in the flag, okay. So this here will generate a flag, and then we test the flag here with the jump equals. So if it was equal to 10, we need to tell it where to jump to. Well, we want it to jump to the end of the program. So what we could do is, again, we could create another label. So we could call that label end prog. So it'll jump to the end of the program. Of course, when you're writing these out, you can always write out different naming structures for yourself, because I don't have a great deal of imagination when it comes to these. I just tend to put the first thing that comes into my head. So that's end prog. So then we need to have end prog label, okay, and then we can put in return tab. Now at the end prog we want to put in the end, okay. So this is our little basic looping structure, and it's going to count up to 10. Now it's interesting to think about where we place this comparison, because we want to really place the comparison at the start, because the value might already be 10, okay. So if we don't want to place it down after the increment, because it'll increment and then, you know, potentially it would go to 11, okay. So we're placing it at this point here, and these are the little things you have to be kind of careful about where you position things within code, but this is the same in high level language as well. So let me go in, and we'll go terminal, run task, and see whether it assembles. So it comes up and it says assembly successful. I was actually hoping it would come up with an error there, so I could go in and I could show you some of the errors, but undoubtedly as we move on to more complex things there will be errors, and we'll be able to see the error codes. Okay, so that's us ran it. I've generated the code, so let's run it in the machine, simulate, and we'll need to get in and load it up first. Edit, and we actually, have we actually got the program there? Edit contents, open, there we go. So that's it there, and I put open, and you can see that we've got our code here. So we'll close that, get in, user panel, simulate, tick enabled, and let's see whether this actually counts up to 10. So when it gets to 10 it should stop and the little red light should come on, and there you go. So 10 in hex is the letter A, okay, so it goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10 is A, and then it goes B, C, D, E, and F, okay. So that has counted up to 10. This is our little looping program, and it's quite fundamental, and it's quite neat, and it's quite powerful. So with just these simple basic commands, so look at the commands we've generated so far. We've had the data command, the add, subtract, multiply, divide. We've got a comparison command. We can do the jump of equals. We've got increment. We've got our normal jump command. We've got the labels here, and we've got our end. So with these basic commands within our registers, we can generate reams of code. I mean, lots and lots of it. So this is all just really basic stuff, but already you could go and download the CPU, and you can download the assembler, and you can generate code for yourself. If this is the kind of thing that floats your boat, then head off to Patreon and you can get all my 3 courses that show you how to build this entire CPU and the assembler, and it shows you so much more. I mean, there's full live mathematics and graphics and string libraries within the machine as well. thank you for listening. On the next video, I'm not sure what I'm going to do because there's so much that we can do, but I'm going to keep it simple and neat and hopefully elegant. I'm not sure about the last one, but I'll do my best. Goodbye.